Welcome to solverfy.
Okay, so we're doing chapter 22, problem 27 here. So we have two thin concentric spherical shells of radii R1 and R2, as seen in this figure, where R2 is obviously greater than R1. And they each contain surface charge densities sigma 1 and sigma 2, respectively. So now we want to determine the electric field for these different scenarios. So first we're going to say at R is less than or equal to R1, or between 0 and R1. So let's do this case first. So now we should see that a Gaussian surface would include no charge here, because the only charge is outside the surface on the spherical shells. So if the charge enclosed is 0, we know that there's going to be no electric field here. Cool. So now we can easily move on. So now for part B, we're going to do the case where R is greater than R1, but less than R2. So now if we draw a Gaussian surface out here, the charge enclosed is going to be all the charge on the first surface. So the charge enclosed on the first surface is given by charge enclosed is the surface area times the surface density. And the surface area of a sphere is 4 pi r squared. So that's the surface area, and times it by surface density, charge surface density. So if this is the total charge enclosed, we draw a Gaussian surface. So let's go ahead and write this out. We know that the electric field is going to be perpendicular to the normal vector at all points. So that means we can easily write this out as the magnitude of E times 4 pi r squared. And this, according to Gauss's law, is equal to Q enclosed over epsilon naught. Rearrange for E, and we see this as Q enclosed over 4 pi epsilon naught r squared. Awesome. So now we just plug in what our Q enclosed is, and that is 4 pi r1 squared. So we see the 4 pi's cancel out, and we're left with sigma 1 r1 squared over epsilon naught r squared. Cool. So that's what the electric field is in between the two shells. So now we can move on to part C, and we're going to do this one for R greater than R2. So for this case, our Q enclosed is now on the first surface plus the second one. So this is sigma 1 R1 squared plus sigma 2 R2 squared, all times 4 pi. So we can put that back into our equation, and we know that the Gaussian surface out here is going to enclose all of those charges. So this just becomes sigma 1 R1 squared plus sigma 2 R2 squared, all over epsilon naught R squared. Awesome. Let's move on to part D now. Oh, actually, let's go back for a second. Let me box this and let you guys write it down. Cool. This equals E. Okay, so now moving on to part D. Part D says under what conditions will E equal 0 for R greater than R2? Well, we already know the equation was given as sigma 1 R1 squared plus sigma 2 R2 squared over R squared epsilon naught. So the only way for this to equal to 0 is if the numerator equals 0, or sigma 1 R1 squared equals negative sigma 2 R2 squared. So yeah, this is the condition that must hold for E to be 0 in that range. Part E says on what conditions will E be 0 for the range we did in part B. So R between R1 and R2. So for this one, our equation was E equaling sigma 1 R1 squared over epsilon R2. And the only way this can be 0, all of these things are non-zero, but sigma 1 could be non-zero if there was no charge. So the only way this can be 0 is if sigma 1 is also 0, which means no charge on the first shell. Another way we could make this 0 is if we put a charge of negative 4 pi R1 squared sigma 1 at the center of the shells. That could also make E 0 because this obviously would just cancel out exactly the case here, but not adding anything to the problem that wasn't already included, you would have to have sigma 1 equaling 0.